As we work our way to the intermediate value theorem, we introduce a new definition, a new type of a set called a connected set. A set A, subset of the real line, is connected if for every two numbers in the set, A and B, C strictly between them implies C is also in the set. So if you've got 2 points and you arbitrarily choose any element in between them, if that also happens to be in the set, that means the entire interval is effectively. So I could say in brackets, what this means is the entire interval, better use parentheses here, is contained in the set. So an alternate definition would be for every two elements in the set, if the set is connected, for every two elements in the set, then the closed interval connecting those two elements is also in the set. So it should be easy to see that on the real line, that's a connected set. And together, these two being the set capital A would not be connected. You could choose an A here, you could choose a B here, but not every point on the real line is between them. So if this is your set, these two intervals, it's not connected. Well, theorem 3.14 kind of goes into more detail about what I just mentioned. If A is connected, then A is one of the following, or it has one of the following forms. It could go from, it could be the interval from A to infinity, or it could be the closed interval from A to infinity, or it could be the interval from negative infinity up to B, or from negative infinity up to B including B. It could also be of the form AB, or AB, or let's see, we'll do it on this side. Let me go. AB, the closed interval. And which one am I missing? AB with the closed on the right and opened on the left. So the open interval, the closed interval, the half open interval, where the open side is either on the B side or on the A side. And then the last one would be, you could write it like this, but I would just write the entire real line. The entire real line is connected. Now my thought was, this is listed in the text just like this. My thought was that, well, let me ask you this. Is the empty set connected? The empty set. Well, we have to go back to the definition. The set is connected if for every A and B in the set, the entire closed interval between A and B is also in the set. So it's definitely true. Why? It's vacuously true. You'll never find 2 points in the set, so you cannot disprove it. If you wanted to claim that the empty set is not connected, you'd have to tell me two numbers in the real line that are in the set, but that the interval between those two numbers is not in the empty set. You can't find that because there are not two numbers in the empty set. So I was going to write the empty set here, but then realized that the empty set is taken care of right here. For every A, B in A, well, the empty set is equal to this. So if A and B are equal, you get the empty set. So the empty set is covered in this right here, but I thought about putting it separately here on item number 3. And the next theorem, we're going to not prove this one because the proof is very similar to a proof we've already seen. The modified Bolzano theorem basically says that in Bolzano's theorem, where f had to be a closed interval. It doesn't have to be a closed interval. Let f be the function from A, domain A, into B. We'll let it be continuous and connected. That's all it needs to be. And the rest of it, I believe, is exactly the same. For any 2 points in A, the domain, with A being less than B, if f of A and f of B have opposite signs, then there exists a C in between them such that f of C is equal to 0.